Right now, as you watch this, something is happening in space that shouldn't be possible. An object spinning through the darkness, tumbling like every other cosmic wanderer we've ever studied, except for one detail that changes everything. Its jet, the brilliant stream of gas and dust that marks it as alive, isn't sweeping across space like it should. Instead, it's locked. Perfectly, impossibly locked on the Sun. And today, December 19th, 2025, as this object makes its closest approach to Earth, astronomers worldwide are staring at their screens with a mixture of fascination and disbelief, because what we're witnessing violates the basic expectations of how nature works. Stay with me for the next several minutes because we're going to walk through the 15th anomaly of Object 3I Atlas, an anomaly so precise, so statistically improbable, that it's forcing the scientific community to ask questions they never thought they'd seriously consider. This isn't about speculation or wild theories. This is about hard data that doesn't fit the models, about measurements that keep pointing towards something we don't yet understand. The object we're talking about entered our solar system from the depths of interstellar space. It's travelling on a path that will take it back out into the cosmic ocean, never to return. For months now, it's been under intense observation from some of the most sophisticated telescopes humanity has ever built, and what they've found has been documented in paper after paper, anomaly after anomaly. But this 15th one, the one we're discussing today, might be the most significant of all, because it suggests a level of precision that natural processes struggle to explain. Here's what makes this so extraordinary. When an object tumbles through space, when it rotates like a football spinning end over end, any feature on its surface should sweep across different orientations. If that object happens to be outgassing, if it's releasing jets of material from specific vents or cracks on its surface, those jets should spray in changing directions as the object turns. Think about holding a spray bottle while spinning in a circle. The water doesn't keep hitting the same spot on the wall, it sweeps around, painting a circle, tracing the path of your rotation. That's what we expect. That's what physics demands. That's what every tumbling comet we've ever studied has shown us. But 3I Atlas doesn't do that. Despite clear evidence of rotation, despite showing all the signs of an object that tumbles through space, its primary jet has maintained alignment with the Sun to within about 8 degrees. For those keeping track at home, that's not a range of orientations. That's not a jet that sweeps and occasionally points sunward. That's a jet that stays pointed at the Sun while the object beneath it spins. Imagine standing in a room, spinning slowly in place, and somehow keeping a laser pointer aimed at a specific spot on the ceiling without moving your hand. You can picture the impossibility of it immediately. Your hand would have to counter-rotate, would have to actively compensate for your body's motion. That's what we're seeing here, except there's no hand, no mechanism we can easily point to that explains this level of stabilization. The observations come from multiple independent sources. We're not talking about one telescope on one night producing questionable data. We're talking about consistent measurements across observation campaigns, from different instruments, under different conditions. The jet orientation has been tracked as the object moved through the inner solar system. The Sun's position relative to the object changed constantly as 3I Atlas travelled along its trajectory. And yet, through all of it, the jet compensated. It adjusted. It maintained that lock. When I first encountered this data, I did what any rational person would do. I looked for the obvious explanations. Maybe the object isn't rotating as much as we think. Maybe there's been a misinterpretation of the light curves, the brightness variations that typically indicate rotation. But the evidence for rotation is solid. The object shows periodic changes in brightness consistent with a tumbling body. Different faces reflect different amounts of light. The rotation is real, so that explanation doesn't work. Maybe the jet isn't as narrowly focused as it appears. Maybe it's actually a broad spray of material, and we're just seeing the densest part, and that densest part happens to be sunward, due to some quirk of how ice sublimates. But the observations show a tightly collimated beam, not a diffuse cloud. The jet has structure, has coherence, has a direction that's measurable and repeatable. So that doesn't work either. Maybe the active region is located exactly at the rotation pole, the point on the object that doesn't move much as it spins, like the tip of a spinning top. That would explain some degree of stability. But here's where it gets even stranger. There isn't just one jet, and they're not coming from the same region. At perihelion, when 3I Atlas made its closest approach to the Sun earlier in its journey, something changed. The original jet, the one that had been active during approach, shut down, and a new jet from a different region on the object's surface activated, And this new jet, this second source of outgassing, also locked onto the Sun. Let me repeat that because it's crucial. 2 different locations on this object, 2 different active regions, both displaying the same behavior, both maintaining alignment with the Sun despite the object's rotation. The odds of having 2 separate vents, randomly positioned on a tumbling body, both just happening to be aligned with the rotation axis in exactly the right way to maintain solar orientation, are astronomical. We're talking about a 1 in 40,000 probability for this dual-pole alignment alone. That's not impossible, but it's deeply improbable, and it's made more so by every other anomaly this object presents. You might be thinking, maybe there's something about the object's shape, or its internal structure, or the way heat moves through it, that naturally produces this effect. Maybe we're witnessing some exotic but natural phenomenon we simply haven't encountered before. That's absolutely possible. Science advances by explaining the unexplained, by finding natural mechanisms for observations that initially seem mysterious, and we'll explore those possibilities in depth as we continue. But here's what you need to understand right now. The precision we're observing isn't just unusual, it's precise in a way that suggests control. It suggests that something about this object, whether internal structure or some mechanism we haven't identified, is actively maintaining this alignment. The scientific papers discussing 3I Atlas use careful language. They present the observations, calculate the probabilities, note the deviations from expected behavior. They don't jump to conclusions. They don't claim to know what's happening. What they do is lay out the data and acknowledge that current models don't fully account for what we're seeing. And that's where we are right now in this moment, as the object passes through its closest approach to Earth. We have data that challenges explanation. We have behavior that strains natural models. We have an object that, by every conventional measure, should not be doing what it's doing. Before we go deeper into this, before we unpack the physics and the implications and the competing theories, I want to ask you something. If you're finding this as fascinating as I do, if you're the kind of person who wants to follow this story as it develops, go ahead and hit that like button. This isn't about boosting an algorithm. Well, okay, it's a little bit about that, but more importantly, it's about building a community of people who care about this kind of deep investigation, who want to think critically about extraordinary observations without dismissing them or sensationalizing them. Drop a comment telling me what you think so far. Are you skeptical? Are you intrigued? Are you waiting for more evidence? I want to know, because we're going on this journey together, and your perspective matters. This is a conversation, not a lecture, and the questions you raise will help shape how we approach the anomalies still to come. Now, with that foundation laid, with that central mystery established, we need to take a step back. Because to understand why this sunward lock is so significant, we need to understand what rotation should look like, what we expect from objects tumbling through the void, and why 3I Atlas's behavior breaks those expectations in such a fundamental way. To grasp why the 15th anomaly matters, you need to understand the baseline. You need to see what normal looks like, because only then does the abnormal reveal itself in full clarity. So let's talk about rotation, about how objects move through space, and about what happens when those objects start outgassing and producing jets. This isn't just abstract physics. This is the foundation that makes the mystery meaningful. Imagine you're standing in your backyard on a summer evening, and you turn on a garden sprinkler. Not one of those modern programmable ones, but the old-fashioned type that spins as water shoots out from its arms. You've seen this. Everyone has. The sprinkler rotates, and as it does, the streams of water sweep across the lawn, creating a circular pattern. The water doesn't somehow stay pointed at one flower bed while the sprinkler spins. It can't. The nozzles are fixed to the rotating body, so the direction they point changes as that body turns. This is intuitive. This is how physical objects work in our everyday experience. Now take that principle into space. When a comet tumbles through the solar system, when its rotation causes different faces to point in different directions over time, any jets erupting from its surface will sweep across space just like those sprinkler streams sweep across your lawn. If the comet completes one rotation every few hours, then the jet's orientation will cycle through a complete revolution in that same time frame. Observers watching from Earth or from orbiting telescopes will see the jet pointing in different directions at different times. Sometimes toward the Sun, sometimes away, sometimes perpendicular, depending on where in the rotation cycle the active vent happens to be. We've observed this behavior countless times. Comet Halley, perhaps the most famous periodic comet, displays exactly this pattern. as it approaches the sun and its ices begin to sublimate, jets erupt from various locations on its potato-shaped nucleus. Those jets sweep across space as Halley rotates. We've mapped this. We've photographed it. We've built models that predict where the jets will point based on the rotation period and the location of active regions. And those models work because the physics is straightforward. The jets are fixed to the surface rotates, therefore the jets rotate. Simple. Or think of a lighthouse on a rocky coast. The light itself doesn't move, but it's mounted on a rotating mechanism, so from the perspective of a ship at sea, the beam sweeps past at regular intervals. You see the flash, then darkness, then another flash as the rotation brings the beam back around. If you were on that ship and you noticed that the lighthouse beam somehow stayed locked on your position, never sweeping away, never losing you despite the rotation you can clearly see in the structure itself, you'd immediately know something unusual was happening. Either the rotation isn't what you think it is, or there's a mechanism compensating for it, or you're misunderstanding the situation entirely. That's the puzzle we face with 3i Atlas. We have clear evidence of rotation. Like curves, the variations in brightness as different surface areas reflect sunlight at different angles tell us the object is tumbling. The physics community isn't debating whether it rotates. That's established. What we're debating is how, despite that rotation, the jet maintains its orientation. How does the lighthouse beam stay locked on the ship? Even Oumuamua, the first confirmed interstellar visitor and an object surrounded by its own set of mysteries, didn't display this kind of behavior. Oumuamua tumbled chaotically, rotating along multiple axes, and while it exhibited non-gravitational acceleration that suggested outgassing, any jets it produced, if they existed, weren't locked in a specific direction. They couldn't be, given the tumbling. The outgassing, if that's indeed what caused the acceleration, would have been diffuse or variable or both. It didn't show the tight collimation and directional stability we're seeing with 3i Atlas. So what could cause a jet to stay pointed in one direction while the object beneath it spins? There are, theoretically, a few possibilities, and we'll explore them in detail later. But right now, understand that none of them are simple. None of them are common. None of them fall into the category of normal cometary behavior. You could have a vent located exactly at the rotation pole, the point that stays relatively fixed as the rest of the object turns around it. That's possible. That's been observed in some comets, where polar vents produce jets that don't sweep as dramatically. But those jets still show some wobble, some variation, because perfect alignment with the pole is rare, and even a slight offset causes precession, causes the direction to drift over time. Or you could have some kind of internal structure that channels sublimating gas through a network of passages, all converging on a single exit point that happens to be aligned just right. But that requires a very specific architecture, a very specific arrangement of voids and conduits, and it still doesn't explain how the system compensates for rotation. The exit might be at the pole, but as the object tumbles, as the pole's orientation changes relative to the sun, the jet direction should still drift unless something is actively maintaining alignment. That word, actively, is key. In normal cometary outgassing, there's nothing active about the directional control. The ice sublimates where the sun heats it. The gas escapes through cracks and vents wherever they happen to exist. The result is jets that reflect the passive structure of the surface, jets that sweep and spray and change direction as the comet rotates. There's no feedback mechanism, there's no adjustment. It's geology and thermodynamics, not control systems. But 3i Atlas appears to be different. Its jet doesn't passively respond to rotation, it maintains direction despite rotation. And that distinction, that difference between passive response and active maintenance, is what makes this anomaly so significant. It's what elevates this from a curiosity to a genuine puzzle that challenges our models. When scientists study comets, they build computer simulations that account for rotation, for surface topography, for ice distribution, for thermal inertia. They input the known parameters and predict where jets should appear, how bright they should be, what directions they should point at different times. And those simulations work remarkably well for typical comets. They reproduce the observed behavior, they match the data. Which means the physics is sound, which means we understand the processes at work. But when you run those same simulations for 3i Atlas, when you input the rotation and the observed jet orientation, the models don't naturally produce the sunward lock. You have to add something, have to tweak the parameters into very specific configurations, have to invoke unlikely arrangements to get the output to match reality. And even then, it's a struggle. This is where we stand as we try to explain what we're seeing. We have models that work for almost everything else. We have physics that predicts behavior accurately across hundreds of observed comets. And then we have 3i Atlas, fitting the pattern in some ways, breaking it completely in others. So the question becomes, is this object an extreme outlier, a 1 in a million natural configuration that just happens to produce this effect? Or is there something fundamentally different about it? Something that requires us to expand our models, to consider possibilities we haven't seriously entertained before. That's the foundation. That's what normal looks like, and why this isn't normal. Now we need to go deeper into the mechanism, into the sunward lock itself, and explore exactly how extraordinary this continuous pointing really is. Let's get specific about what we're actually observing here, because the details matter, and it's in the details that the true strangeness emerges. The jet from 3i Atlas isn't just roughly pointed toward the sun, it's maintaining alignment to within about 8 degrees across observation periods spanning weeks. That's not a vague tendency, that's precision. That's a level of consistency that demands explanation. To put that in perspective, imagine you're holding a flashlight and someone asks you to keep the beam pointed at a spot on the wall while you spin in a slow circle. Not impossible, right? You can do it by moving your arm, by compensating for your body's rotation, by actively tracking the target. But now imagine you're not consciously thinking about it. Imagine the flashlight somehow stays locked on that spot without you deliberately adjusting. Imagine you're spinning, and the beam compensates automatically, without your awareness, without visible effort. That's the kind of behavior we're seeing. The object rotates, but the jet direction adjusts to maintain solar alignment, and there's no obvious mechanism for how. The compensation occurs. The sun's position relative to 3i Atlas changed constantly as the object travelled through the inner solar system. The geometry shifted, the angles evolved, and yet, through all of that, the jet adjusted its orientation to track the sun's position. This isn't a static situation where the object happened to be oriented in a lucky direction at one moment. This is dynamic tracking over extended time periods. The jet didn't just point sunward once. It kept pointing sunward as the object's position changed, as its distance from the sun varied, as it moved through different regions of space. Astrophysicists use a concept called thermal lag to explain some aspects of cometary behavior. When sunlight heats a comet's surface, there's a delay before the ice beneath that surface warms enough to sublimate and produce jets. This lag means that the most active regions aren't always the ones directly facing the sun at that exact moment. They're offset, rotated slightly ahead or behind depending on the rotation direction and the speed of heat penetration. This thermal lag can cause jets to appear at angles relative to the sun's direction, and it's a well-understood phenomenon that models account for. But thermal lag operates on timescales of hours to days. It explains offsets of tens of degrees as the heated region rotates into the shadow and a newly heated region begins outgassing. It doesn't explain sustained multi-week alignment. It doesn't explain why a jet would continuously adjust to stay pointed at the sun, rather than sweeping through a range of orientations dictated by the rotation period. Thermal lag is part of the story for typical comets, but it's not sufficient to explain what 3i Atlas is doing. Think about the heat distribution on a rotating object in space. As the object spins, different parts of its surface enter and leave sunlight. The side facing the sun heats up. The side facing away cools down. If there's ice present, the heated side sublimates and produces outgassing. The cooled side, unless it has some residual heat from before, stays relatively inactive. This creates a day-night cycle on the object's surface, even though it's moving through space rather than orbiting with a fixed day side. For a normally rotating comet, this means jets turn on and off, or vary in intensity, as active regions rotate into and out of sunlight. You get periodic behavior, jets that pulse or flare as the rotation brings fresh ice into the heated zone. And again, we've observed this many times. It's standard, it's expected, but it produces jets that sweep, that change direction, that reflect the underlying rotation. The spotlight metaphor works here. Imagine a spotlight mounted on a rotating platform. As the platform turns, the spotlight illuminates different areas. Sometimes it's shining north, sometimes east, sometimes south, then west, cycling through directions as the platform completes each revolution. Now imagine that spotlight somehow always illuminates the same person, no matter where they move in the room, no matter how the platform rotates. The beam bends or swivels or compensates through some mechanism, but the end result is constant tracking. That's what we're seeing with 3i Atlas. The spotlight tracks the sun. The beam doesn't sweep, it compensates. One of the most puzzling aspects of this is what it implies about the object's internal structure. For the sunward lock to work, for a jet to maintain orientation despite rotation, you need certain conditions. Either the active region is positioned at a location that naturally stays pointed in one direction, which means the rotation pole, or there's internal channeling that redirects gas flow regardless of surface orientation, or there's some mechanism we haven't identified that controls the outgassing in response to rotation. Let's explore that first option. If the active vent is located at the rotation pole, it would experience minimal directional change as the object spins. Think of the Earth's axis. The North Pole doesn't sweep around as the Earth rotates. It stays relatively fixed in space, pointing toward Polaris, the North Star. If you had a geyser at the North Pole, its plume would maintain a consistent direction, even as the planet turned beneath it. So in theory, a polar vent on 3i Atlas could explain the directional stability. But here's the problem. For a polar vent to track the sun, the rotation pole itself has to stay pointed at the sun. And as the object moves along its orbit, as its position relative to the sun changes, the pole's orientation would have to adjust to maintain that alignment. Rotation poles don't normally do that. They maintain their orientation in inertial space. The Earth's axis points toward Polaris not because Polaris is special, but because the axis is stable, locked in that direction by angular momentum. Changing a rotation axis requires torque, requires external force, requires something pushing or pulling on the object in a way that alters its spin. Could such a torque exist? Absolutely. Outgassing itself produces torque. When jets erupt from one side of a comet, they create a reaction force like a tiny rocket engine, and that force can alter the rotation over time. We've seen this. We've measured it. Comets spin up or spin down or change their axis orientation due to jetting torques. But those changes are gradual, and they're typically chaotic, not precisely directed. For outgassing torques to maintain a sunward pointing pole, you'd need the jets positioned and timed in exactly the right way to produce corrective force whenever the pole starts to drift. That's possible in theory, but it requires either extraordinary luck or a feedback system that adjusts jet activity based on orientation. And remember, there's not just one jet. At perihelion, the close approach to the sun, the original jet shut down, and a new jet from a different location activated. This second jet also maintains sunward orientation, so now you need two rotation poles, or two regions that both happen to have the right geometry, or a system that can switch between them while preserving the alignment. The coincidences stack, the improbabilities multiply. There's another layer to this that's worth examining. When sunlight hits the surface of an icy object, it doesn't instantly penetrate deep into the interior. There's a layer of dust and refractory material, a crust that insulates the ice beneath. Heat conducts slowly through this layer, so when a new region rotates into sunlight, there's a delay before it gets hot enough to produce significant sublimation. Similarly, when a region rotates out of sunlight, it doesn't immediately freeze solid. It retains heat for a while and can continue outgassing even in shadow. This thermal inertia means that the day-night boundary on a comet isn't sharp. There's a twilight zone where recently heated material continues to release gas. For most comets, this creates a complex pattern of activity, with jets turning on gradually, peaking in intensity, then declining as the heat dissipates. It's not like flipping a light switch, it's more like the cooling coils on a stove, glowing and radiating heat long after you've turned off the burner. But with 3i Atlas, the observed jet behavior suggests something more abrupt, more responsive than typical thermal inertia would predict. The jet maintains tight collimation and consistent orientation, not the diffuse, variable spray you'd expect from a broad region of gradually sublimating ice. It's as if the active area is small, focused, and turns on and off more decisively than the slow heat diffusion model would suggest. Some researchers have proposed that this could indicate deep vertical vents, channels extending far below the surface, insulated from the cold of space by surrounding material. In such a structure, sunlight would heat the opening of the vent, and that heat would conduct downward to ice reserves far below. The sublimating gas would then travel up through the channel and exit in a collimated beam like a natural rocket nozzle. The insulation provided by the depth and the surrounding material would keep the base of the vent cold when the opening is in shadow, preventing diffuse outgassing from the night side. This is plausible. This could work. But it requires a very specific internal architecture. It requires the vent to be aligned with the rotation pole, or close enough that rotation doesn't significantly change the exit direction. And it requires this configuration to exist not just once, but twice, in two different locations that both happen to activate at the right times and both happen to maintain sunward alignment. The probability isn't zero, but it's low. It's the kind of scenario that makes you wonder whether we're missing something, whether there's a piece of the puzzle we haven't identified yet. I want to be clear about something. Nothing I've described so far is impossible from a natural perspective. Complex internal structures exist. Lucky orientations happen. Rare configurations occur. The universe is vast, and across billions of objects, even wildly improbable arrangements will eventually manifest somewhere. But the question we're grappling with is whether this particular arrangement, with this particular precision, occurring in this particular object that already displays 14 other anomalies, represents that natural edge case, or whether it's evidence of something we need to think about differently. As we watched 3I Atlas approach the Sun, as it passed through perihelion and emerged on the other side, the behavior of these jets became the focus of intense scrutiny. Telescopes tracked every fluctuation, every change in brightness, every shift in the plume's structure. And what they found at that critical moment, at the point of closest solar approach, is what we need to discuss next. Because it's there that the 15th anomaly crystallized into something undeniable. There are moments in science when an observation moves from interesting to profound, when data stops being a curiosity and becomes a challenge, a line in the sand that demands response. For 3I Atlas, that moment came at perihelion, not at the moment of closest approach itself, but in what happened afterward, in the geometric transformation that occurred as the object rounded the Sun and began its outbound journey. This is where the 15th anomaly revealed its full implications, where the pattern became impossible to dismiss as coincidence. Let's set the stage. As 3I Atlas approached the Sun, its primary jet, the one we've been discussing, was active and maintaining its sunward orientation. The object was diving inward along its hyperbolic trajectory, heating up, outgassing, intensifying, all according to the familiar script of cometary behavior. Observers tracked it through every phase of the approach, documenting the jet's activity, measuring its brightness, analyzing its spectrum. Everything was being recorded, archived, made available for analysis. Then came perihelion, the point of closest approach. This is when solar heating reaches its peak, when the surface temperature spikes, when sublimation rates hit their maximum. For most comets, perihelion is a crescendo of activity, a spectacle of outgassing and dust production. And 3I Atlas didn't disappoint in that regard. It brightened, it flared, it displayed all the energetic behavior you'd expect from an icy body experiencing maximum solar flux. But then, as it emerged from perihelion and began moving outward, something changed. The geometry of the situation had shifted. Before perihelion, the object was approaching the Sun, and the jet pointing toward the Sun was pointing back along the trajectory, back toward where the object had come from. After perihelion, as the object started moving away, that same geometric orientation would mean the jet should now point behind the object, pointing back at the Sun but also back along the outbound path. Except that's not what happened. The original jet, the one that had been active throughout the approach, shut down. Not gradually, not over weeks as the object cooled, relatively quickly by astronomical standards. The primary source of outgassing from the approach phase ceased, and in its place, a new jet activated. Not from the same region, not from a vent that had simply changed its output direction, from a different pole, a different location on the object's surface, and this new jet, this secondary source, also pointed at the Sun. Take a moment to absorb that. Two active regions located on opposite sides or poles of the object. The first one dominates during approach, maintaining sunward orientation. Then, when the geometry changes at perihelion, when that same orientation would no longer serve the same function, the first jet turns off and a second one turns on, also sunward, oriented but positioned to maintain alignment given the new trajectory geometry. It's like watching someone walk into a room, turn on a light to illuminate their path. Then when they pass the center point and start walking the other direction, they switch off the first light and turn on a different one behind them, ensuring continuous illumination of their forward path. The precision required for this switching behavior is staggering. Let's talk probabilities, because numbers help ground us when dealing with the extraordinary. For a single vent to be positioned such that it maintains sunward orientation despite rotation, you need specific geometric alignment. The odds of this happening by chance depend on how many active regions exist on the object, and how they're distributed, but we're looking at something in the range of 1 in a few hundred for favourable positioning. Now, for two vents, positioned at different poles, both to maintain sunward orientation during their respective active phases, and for them to switch activity at the right time to ensure continuous tracking, you're multiplying probabilities. The calculation isn't simple because it depends on assumptions about the object's structure and composition, but multiple analyses have converged on odds in the range of 1 in 40,000. Not impossible, but deeply, profoundly unlikely. 1 in 40,000. Think about what that means. If you had 40,000 randomly tumbling comets with multiple active vents, you'd expect to see this dual pole alignment pattern in one of them. Across the entire population of comets we've studied, across centuries of observation, we haven't seen this behavior before, and now it appears in an interstellar object, an interloper from beyond our solar system, an object that already displays a constellation of other anomalies. The coincidence strain grows heavier. I want to walk you through the mechanism that would have to exist for this to occur, naturally. First, you need two deep reservoirs of ice, positioned at or near opposite poles of the object. These reservoirs need to be connected to surface vents through channels, or cracks that allow sublimated gas to escape. The channels need to be insulated enough that when one pole is in shadow, the ice there stays frozen and inactive, while the pole in sunlight heats up and outgasses vigorously. At perihelion, as solar heating peaks, both poles are receiving elevated thermal input, but the geometry of illumination is shifting rapidly. The object is moving fast at closest approach, so the angle of sunlight relative to the surface changes on short timescales. In this scenario, one pole begins to rotate out of optimal illumination. The vent there, which has been active, starts to receive less direct sunlight, or the angle becomes less favourable for heat penetration into the internal reservoir. Meanwhile, the opposite pole rotates into better illumination. The vent there, which had been dormant because it was poorly positioned before perihelion, now starts to heat up. The first vent shuts down as its reservoir cools and sublimation rates drop. The second vent activates as fresh ice begins to warm, and by chance, by the specific geometry of how these vents are positioned, relative to the rotation axis, both happen to maintain sunward orientation during their active phases. The transition occurs over days to weeks, fast enough that observers see a clear switch rather than a long overlap, but not so fast that it violates what we know about thermal inertia and sublimation timescales. That's the natural explanation. That's the scenario that doesn't require anything extraordinary beyond unlikely geometry, and I want to be clear. This could be what's happening. Science doesn't demand that unlikely events never occur. It acknowledges that low probability outcomes manifest in reality, especially when you're observing a large number of events. If we've studied thousands of comets and millions of asteroids, and now we're examining interstellar visitors, seeing a 1 in 40,000 configuration isn't absurd. It's rare but not impossible. But here's where the discomfort creeps in. This isn't happening in isolation. The dual pole alignment is the 15th anomaly, not the first. It's occurring in an object whose trajectory through the solar system has odds of approximately 1 in 200, 0.5%, of happening by chance. It's occurring in an object with chemical composition anomalies, with velocity characteristics that don't match natural expectations, with a tightly collimated outflow that looks more like a focused beam than a diffuse cloud. When you start stacking these probabilities, when you multiply 1 in 500 by 1 in 40,000, you enter territory where the natural explanation, while possible, requires you to accept that you're witnessing an accumulation of rare events in a single object. There's a principle in reasoning, often attributed to Sherlock Holmes but rooted in older logic, that says when you have eliminated the impossible, whatever remains, however improbable, must be the truth. But the corollary to that principle is equally important. Before you conclude that something improbable is true, you must genuinely eliminate the alternatives, not just find them uncomfortable or difficult to verify. We're not at the point of elimination yet. We're at the point of accumulation, where the data is piling up, where each new observation adds weight to the scale, and where both the natural and the extraordinary explanations are still on the table. The switch at perihelion does one thing unambiguously. It rules out certain simple explanations. It rules out the idea that the sunward orientation is merely a lucky frozen snapshot, a static configuration that happens to look impressive at one moment but would dissolve under extended observation. The switch demonstrates dynamic behavior, demonstrates that the system responds to changing conditions, that there's a pattern to the activity beyond random outgassing. Something about this object's structure or composition or internal mechanism produces this dual alignment behavior, and whatever that something is, it's not a feature we've encountered before in a natural comet. Imagine if you were an engineer designing a probe to travel through interstellar space and you wanted it to maintain solar orientation for maximum power generation or thermal management. You might design it with two sets of attitude control jets, one for inbound trajectory and one for outbound, each positioned to provide corrective thrust based on the sun's position. You might set up a system that activates the appropriate set based on trajectory phase, shutting down the first when it's no longer optimally aligned and activating the second as the geometry changes. What we're observing with 3i Atlas is consistent with that kind of dual system design. But we're not supposed to be looking at an engineered probe. We're supposed to be looking at a comet, a chunk of ice and rock wandering through space, shaped by accretion and impact, governed by sublimation and thermodynamics, and that's the tension. The behavior looks designed. The probabilities suggest rarity beyond expectation. But the object is presenting itself as natural, outgassing like a comet, following a trajectory that, while unusual, is gravitationally sound. So where does that leave us? It leaves us with questions. It leaves us with data that doesn't fit comfortably into existing frameworks. It leaves us watching, analysing, waiting for more information that might tip the balance one way or another, because this isn't over. The story of 3i Atlas is still being written, and today, as it makes its closest approach to Earth, as telescopes capture the highest resolution data we've yet obtained, we're gathering the information that might finally provide answers, or at least better questions. And speaking of questions, the ones raised by this perihelion switch lead us directly into the next layer of the mystery. What this precision implies about the object's internal nature. Precision is the signature of constraint. When a system behaves with precision, when it maintains tolerances, when it repeats patterns within narrow margins, that precision tells you something about the underlying structure. It tells you that there are forces or mechanisms limiting deviation, channeling behavior, enforcing regularity. And when you observe precision in a context where you expect chaos or randomness, when you see order emerging from what should be disorder, that's when you need to start asking deeper questions about what's really going on. The 8-degree alignment tolerance that 3i Atlas maintains between its jet and the sun's direction is a form of precision. It's not perfect alignment, not zero deviation, but it's tight enough to demand explanation. In a system governed purely by random orientation and passive thermal response, you'd expect to see the jet sweeping through a full range of angles dictated by the rotation period. The fact that it doesn't, the fact that it stays within a narrow cone of directions all centered on the sun, means something is constraining the system. What could provide that constraint? Let's think through the possibilities systematically, because this is where we move from observation to interpretation, from data to models, and where the competing explanations begin to diverge. The first and most conservative explanation is internal structure. Maybe the object's interior isn't uniform. Maybe it contains channels, voids, passages carved by some process during its formation or history. These channels could guide sublimating gas from deep internal ice reservoirs to surface vents positioned in specific locations. If those locations happen to be at or near the rotation poles, and if the channels are insulated by surrounding material, you could get focused jets that don't sweep as dramatically with rotation. The gas travels through the channels, picks up speed in the confined space, exits through narrow vents, producing collimated beams. The insulation prevents heat from reaching ice on the night side, so outgassing only occurs from vents currently in sunlight. And if the vents are polar, their orientation stays relatively stable despite the body's rotation. This is geologically plausible. We know that comets have complex internal structures. We've sent probes to study them up close. The Rosetta mission revealed that Comet 67P has distinct layers, voids, cliffs, and regions of varying composition. There's no fundamental reason why deep channels couldn't exist, carved by ancient sublimation, or formed during the object's assembly from smaller components. So the structure explanation isn't exotic, it's within the bounds of known cometary science. But here's the issue. For this structure to produce the observed dual-pole switching behaviour, you need both vents positioned just right, both connected to substantial ice reservoirs, both insulated effectively, and both oriented such that they maintain sunward alignment during their respective active phases. That's a lot of specific requirements. Each one is plausible in isolation, but requiring all of them simultaneously is where the probability calculation starts to hurt. Let's consider thermal management. For a vent to turn on and off as decisively as the perihelion switch suggests, the thermal response needs to be fairly sharp. You need the ice feeding that vent to heat quickly when illuminated and cool quickly when shadowed. Typical thermal inertia would smooth this out, creating gradual transitions, overlapping activity between the two vents rather than a clean switch. So either the thermal properties of the material are unusual, providing less buffering than expected, or the reservoirs are positioned such that they respond rapidly to changes in illumination. One way to achieve rapid response is through direct exposure. If the ice is close to the surface at the vent location, sunlight doesn't have to conduct through thick layers of insulating dust. It hits the ice directly, sublimates it quickly. But this creates a different problem. If the ice is that close to the surface, it should erode rapidly, especially at perihelion when solar flux is maximum. You'd expect the vent to evolve, to change character, potentially to shut down permanently as the ice is depleted. For the system to remain active through perihelion and then switch to the second vent, both reservoirs need to be substantial, not just surface frost. So maybe the vents are surface level but the reservoirs are deep, connected by those channels we discussed. The surface ice sublimates quickly, exposing a channel opening. Gas from the deep reservoir flows up through the channel, exits rapidly. This provides both the collimation and the rapid thermal response, but it also requires that the channel doesn't clog, doesn't collapse, doesn't get buried by dust and debris from the sublimating surface. It requires stability in a dynamic environment. Another possibility that some researchers have explored is selective activation based on composition. Maybe the two poles have different ice mixtures. Maybe one is dominated by water ice, the other by more volatile species like carbon monoxide or carbon dioxide. These volatiles sublimate at different temperatures, so as the object approaches the sun and heats up, the more volatile pole activates first, outgassing vigorously even at greater solar distances. Then at perihelion, as temperatures peak, the waterous pole begins to dominate because water sublimation rates finally become competitive. Post-perihelion, as the object cools, the water pole shuts down first, and the volatile pole, which sublimates at lower temperatures, remains active longer. This compositional gradient could explain the timing of the switch, but it still doesn't explain the orientational precision. Why would the volatile pole and the water pole both happen to be positioned such that their jets point sunward? You're still relying on geometric coincidence, just with an added layer of compositional explanation for the timing. I keep coming back to that word coincidence, because it's the crux of the debate. How many coincidences can you stack before the explanation stops being satisfying? There's no hard rule, there's no objective threshold where you're forced to reject natural explanations, but there's a psychological and logical discomfort that grows with each added requirement, each additional unlikely element that has to be invoked. And when you're already dealing with an object that has 14 other anomalies, each requiring its own set of specific conditions to explain naturally, the cumulative weight becomes significant. Let me present the alternative framing, not as a conclusion but as a comparison. If you were to design an object to maintain sunward orientation, to use solar heating as a power source or a thermal management tool, how might you do it? You'd position active elements at opposite poles. You'd engineer them to respond to illumination changes. You'd set up a switching mechanism so that the optimal element for each trajectory phase is active, while the other is dormant. You'd collimate the outflows to maximize efficiency, to direct the gas in specific directions for thrust or heat dissipation, and you'd build in thermal insulation so that the dormant side stays inactive, not wasting resources. What we're observing matches that design pattern, not perfectly because there's noise, there's variation, there's the messiness of real-world observation. But the core behavior, the dual-pole alignment with phase-appropriate switching, is consistent with intentional design. That doesn't prove design. Consistency is not proof, but it means the question is legitimate, is worth asking, is not automatically dismissible as fringe thinking. The scientific method doesn't favour one explanation over another based on philosophical preference. It favours explanations that fit the data with the fewest assumptions, that make testable predictions, that can be evaluated against new observations. Right now, both the natural and the design explanations are on the table. Both require assumptions. The natural explanation requires stacking multiple low-probability geometric and compositional coincidences. The design explanation requires accepting that what appears to be a comet might be something else, something manufactured, something that travelled here from another star system. Neither is comfortable, neither is simple, and that's where we sit in the space between competing models, waiting for data that might favour one over the other. Because precision, while it demands explanation, doesn't dictate which explanation is correct. It just tells us that the system is constrained, that there's structure beneath the behaviour, and that understanding that structure is key to understanding the object itself. And as we try to understand this particular structure, we can't ignore the fact that it exists within a broader context, a constellation of anomalies that all point in similar directions, all raise similar questions. That context is what we need to explore next. An anomaly in isolation is a curiosity. A pattern of anomalies is a signal. And what we're dealing with in 3i Atlas isn't one strange observation that stands alone. It's a collection, a cluster of behaviours and characteristics that deviate from expectations in ways that reinforce each other, that create a coherent picture, even if we don't yet know what that picture depicts. The 15th Anomaly, this dual-pole sunward lock, doesn't exist in a vacuum. It's part of a larger tapestry, and to understand its significance, we need to see how it connects to everything else this object has shown us. Let's start with the trajectory, because that's where the strangeness began, before we ever observed jets or measured rotation or analysed composition. When 3i Atlas was first identified as an interstellar interloper, astronomers traced its path backward, reconstructing where it came from and what route it took to get here. And what they found was unsettling in its precision. The object didn't just wander into our solar system from some random direction. It came in along a trajectory that brought it remarkably close to the plane of the solar system, that aligned with the orbital paths of the major planets, in a way that natural interstellar objects almost never do. You have to understand space is three-dimensional and mostly empty. The solar system occupies a flattened disk, the ecliptic plane, where the planets orbit in rough alignment because they all formed from the same rotating disk of gas and dust. But objects coming from interstellar space have no reason to arrive aligned with this plane. They come from random directions, from stars scattered throughout three-dimensional space. The odds of an interstellar visitor naturally arriving at a trajectory angle matching the ecliptic to within a few degrees are approximately 1 in 200%. But 3i Atlas did exactly that. Its trajectory brought it into the inner solar system along a path that was nearly coplanar with the planets. Not exactly aligned, but close enough that the probability calculation raises eyebrows. And that was just the first anomaly, the first hint that this object might be unusual. Some researchers propose that maybe it had been gravitationally deflected by a previous stellar encounter, bent from its original path into this convenient alignment. But modelling those scenarios requires very specific conditions, and the probability doesn't improve much. Then came the velocity. Interstellar objects move fast because they're not bound to the sun's gravity. They're passing through, and their speed reflects the orbital motion of their home star around the galactic centre plus whatever ejection velocity sent them into interstellar space. But they also slow down as they approach a star due to that star's gravity, then speed back up as they leave. The velocity profile is predictable based on the trajectory and the mass of the star. 3i Atlas showed a velocity excess. Not a huge one, but measurable, consistent, there in the data. It was moving slightly faster than a purely gravitational trajectory would produce. This is where the outgassing comes in, because sublimating gas acts like a rocket exhaust providing thrust, but the direction of that thrust matters. For most comets, outgassing happens from multiple vents in various orientations, and the net thrust is often chaotic or minimal because the forces partially cancel out. For 3i Atlas, the velocity excess suggested directed thrust, a net force pushing in a consistent direction, and the analysis showed that this direction was close to the solar alignment, meaning the object was being accelerated in a way that matched the sunward jet orientation. So now we have trajectory alignment, velocity excess, and directed thrust, all connected to each other, all pointing toward behavior that's unusual but potentially explainable if the jet orientation is stable and aligned. Which brings us back to the 15th anomaly. The sunward lock isn't just a strange observation, it's the mechanism that could explain the velocity anomaly. The dual-pole system, with jets always pointing toward or away from the sun depending on trajectory phase, would produce exactly the kind of directed thrust needed to account for the measured velocity excess. The pieces fit together. But fitting together doesn't equal natural inevitability. It means the anomalies are part of a coherent system, which could be a naturally coherent system, a set of geometric and compositional coincidences that happen to create consistent behavior. Or it could be an intentionally coherent system, designed to function in a specific way. Both interpretations are supported by the same data fitting together. Now let's talk about composition. Spectroscopic analysis of 3I Atlas, measurements of the light reflected and emitted by the object and its jets, revealed chemical signatures that were unexpected. The gas composition showed elevated levels of certain volatiles that don't typically dominate cometary outflows. The dust-Togas ratio was off, different from what most comets in our solar system display. Some of this can be explained by the object's interstellar origin. It formed around a different star in a different protoplanetary disk, with a different mix of elements and compounds. Of course it would have a different composition. That's expected. But the specific composition, the particular mix of elements, didn't quite match models of interstellar chemistry based on what we know from observations of molecular clouds and protoplanetary disks around other stars. It was within the broad range of possibility, but it was sitting at the edge of that range, in territory that required specific formation conditions. Another low probability configuration, not impossible, but adding to the accumulation of oddities. Then there's the anti-tail. Comets sometimes display multiple tails, including dust tails that can appear to point in unexpected directions due to orbital geometry and the curvature of the dust trail. But 3I Atlas showed a feature that looked like a backward-pointing jet, a stream of material moving in the opposite direction from what the solar wind and radiation pressure would naturally produce. This feature was fainter than the primary jet, harder to observe, but it was there, documented in multiple images. The explanation offered was that this could be a perspective effect, an artifact of viewing geometry, where we're seeing a curved dust trail from an angle that makes it appear to point backward. Or it could be a real retrograde flow, possibly from a vent on the night side where gas sublimates and expands in the direction opposite to the sun-facing jet. Either way, it's unusual. It's not something most comets show. It adds another layer to the behavioral pattern. The jet collimation is another piece. Most cometary jets are broad, diffuse, spreading out in wide cones as the gas and dust escape from surface vents. But the primary jet from 3I Atlas is tightly collimated, maintaining a narrow beam shape over considerable distance. Collimation can occur naturally if the vent geometry acts like a nozzle, if the surrounding topography channels the flow. But tight collimation over long distances requires sustained pressure gradients, requires the gas to stay focused rather than dispersing. It's achievable naturally, but it's more typical of engineered systems, of rocket exhaust plumes, of directed flows. Let me give you the probability stack. Trajectory alignment with the ecliptic, roughly 1 in 500. Dual-pole sunward orientation with perihelion switching, roughly 1 in 40,000. When you combine these, you multiply the probabilities assuming they're independent events. 1 in 500 times 1 in 40,000 is 1 in 20 million. But they're not entirely independent because the jet orientation affects the trajectory through thrust. So the calculation is more complex, but the combined odds are still in the range of 1 in 20 million. When you account for all the factors properly, 1 in 20 million, that's the natural probability space we're occupying. Not zero, not impossible, but extraordinarily unlikely. And that's before you add in the compositional anomalies, the velocity excess, the collimation, the anti-tail, and all the other smaller oddities documented in the observation logs. Each one individually can be explained. Each one adds a multiplier to the combined probability. Here's the thing about probability. It's a tool, not a verdict. Low probability doesn't mean an event can't happen naturally. It means that if it does happen, you are witnessing something rare. And rarity has value. Rare events teach us about the edges of possibility, about the extreme configurations that nature can produce. Studying 3I Atlas, even if it turns out to be entirely natural, will expand our understanding of cometary physics, of interstellar object formation, of the diversity of planetary system architectures. That's valuable regardless of interpretation. But probability also informs investigation priority. When you have an object with 1 in billions odds, you look harder. You allocate more telescope time. You bring in more experts. You apply more scrutiny. Because either you're documenting an extreme natural outlier, which is scientifically important, or you're documenting something else entirely, which would be paradigm shifting. Either outcome justifies the attention, and that's where we are. The attention is justified. The investigation is warranted. The questions are legitimate. The connections between anomalies matter because they show coherence. The trajectory alignment makes sense if the object has directed thrust. The directed thrust makes sense if the jets are oriented consistently. The consistent orientation makes sense if there's internal structure maintaining alignment. The structure makes sense if the composition includes materials that sublimate selectively. Each piece supports the others. They form a logical chain. But logical chains can be either causal or coincidental. Causal means one thing leads to another, means there's a mechanism connecting them. Coincidental means they just happen to align, means multiple independent factors lined up by chance. Distinguishing between causation and coincidence requires more data, requires predictions that can be tested, requires observations that would definitively favour one model over another. What would such observations look like? If the natural model is correct, we should eventually detect variations in the jet alignment. We should see wobble, precession, changes in orientation as thermal cycles shift the active regions. We should find that the internal structure, if we can probe it through radar or seismic techniques, shows the expected channels and reservoirs. We should discover that the compositional anomalies correspond to specific formation scenarios that match the object's presumed origin. If the alternative model has merit, we should find that the alignment remains stable beyond what thermal and structural models predict. We should detect signatures of materials or configurations that don't match natural formation pathways. We should observe behaviors that suggest active control, responses to conditions that natural systems wouldn't respond to. And we should be open to the possibility that some observations might not fit either model cleanly, that we might need to revise our understanding in ways we haven't anticipated. Right now, at this moment in the investigation, we're in data collection mode. The object is at its closest approach to Earth. The best telescopes humanity has built are trained on it. Spectrometers are analysing its light. Infrared instruments are mapping its thermal profile. Radio telescopes are searching for any anomalous emissions. And over the coming weeks, that data will be processed, analysed, peer-reviewed and debated. Answers will start to emerge, or at least better questions will crystallise. The 15th Anomaly connects to all of this because it's both evidence and explanation. It's evidence of unusual behaviour, and it's a potential explanation for other anomalies like the velocity excess. It ties the pattern together, makes the system coherent, and whether that coherence reflects natural complexity or something else, it's what makes 3i Atlas one of the most important objects we're currently studying. Because understanding it means understanding not just this one visitor, but the broader possibilities of what can exist, what can form, and what might be travelling between the stars. And speaking of natural possibilities, we need to dig into those explanations more deeply to give them the fair examination they deserve. Let's be rigorous here. Let's Steelman the natural explanation, which means presenting it in its strongest possible form, giving it every benefit of doubt, and examining whether it can account for what we're observing. Because science doesn't progress by dismissing conventional explanations prematurely. It progresses by testing them thoroughly, by identifying where they succeed and where they struggle, and by being honest about both. The natural formation hypothesis for 3i Atlas goes something like this. The object formed in a protoplanetary disk around a distant star, billions of years ago when that star was young and surrounded by the raw materials for planet formation. During this formation period, through collisions, accretion, and thermal processing, the object developed an internal structure that included ice reservoirs at different depths and locations. Some of these reservoirs became connected to the surface through cracks and channels, pathways created by thermal stress or impact events, or sublimation of overlying material. The object's rotation was established early, either from the angular momentum of the colliding bodies that formed it, or from subsequent torques applied by impacts or outgassing. Over billions of years, this rotation might have evolved, might have changed due to various forces, but by the time the object was ejected from its home system, either through gravitational interactions with planets or close encounters with other stars, it had settled into the tumbling pattern we observe today. Ejection into interstellar space would have been traumatic. The velocity required to escape a stellar system is substantial, and achieving it means the object experienced strong gravitational interactions. These interactions could have altered its structure, could have opened new fractures, could have repositioned internal components. But once in interstellar space, once travelling through the cold and dark between stars, the object would have become thermally stable, frozen solid, inert. Then it encountered our solar system. The gravitational pull of the sun bent its trajectory, brought it inward. Solar heating began to affect the surface. Volatile ices, frozen for billions of years, started to warm. At some distance from the sun, the surface temperature rose high enough for sublimation to begin. Gas started to escape from the warmest regions, from cracks and vents that provided pathways to internal reservoirs. This is standard cometary activation, nothing unusual so far. But the specific geometry of the vents, the particular orientation of the channels, happened to be aligned in such a way that the initial outgassing produced a jet roughly pointing toward the sun. This wasn't intentional. It was luck, geometry, the random outcome of how the object's structure and rotation axis happened to be oriented relative to the sun when sublimation became significant. The alignment wasn't perfect, but it was close, within those 8 degrees that define the observed tolerance. As the object continued inward, as heating intensified, the jet remained active because the vent was positioned such that it stayed in favourable illumination. Maybe it was near the rotation pole, so it didn't sweep through large orientation changes. Maybe the rotation period was such that the vent cycled through day and night slowly, maintaining relatively stable output. Either way, the jet persisted, maintained its rough alignment, produced the directed thrust that caused the velocity anomaly. At perihelion, peak heating caused changes. The original vent, which had been dominant during approach, experienced maximum thermal stress. Maybe the surrounding surface eroded away, exposing different geometry. Maybe the ice feeding that vent depleted in the intense heat. Maybe thermal expansion cracked the structure, shifting the gas flow. For whatever reason, the first jet declined in activity. Meanwhile, on the opposite side of the object, a different vent that had been dormant began to activate. This vent connected to a different reservoir, one that required higher temperatures to sublimate significantly, or one that had been shielded from heating until the geometry at perihelion exposed it to direct sunlight. This second vent also happened to be positioned near a rotation pole, also happened to be aligned such that its outgassing pointed roughly sunward. Again, luck, geometry, the outcome of internal structure that we can't directly observe but can infer from behaviour. The switch wasn't coordinated, it was responsive, driven by temperature changes, by sublimation rates, by the passive physics of heat and phase transitions. But the timing and the geometry, by chance, produced the appearance of intentional switching. That's the natural hypothesis in its strongest form. It requires multiple low-probability alignments, but it doesn't require new physics. It doesn't invoke unknown mechanisms. Everything in this scenario is within the bounds of what we know comets can do, pushed to the extremes of probability space, but not beyond it. And here's the critical point. This hypothesis is testable. It makes predictions. If it's correct, we should see certain things in the data and not see others. We should see thermal inertia effects. The switch at perihelion shouldn't be instantaneous. There should be a transition period where both jets overlap, where the first is declining and the second is rising, reflecting the time it takes for heat to penetrate and for sublimation rates to respond. We should see variations in the jet alignment. Even polar vents wobble slightly due to precession, due to small offsets from perfect polar positioning. The 8-degree tolerance should occasionally be exceeded, should show scatter, should reflect the imperfect nature of natural alignment. We should see compositional evidence for multiple reservoirs. Spectroscopy should reveal differences in the gas chemistry between the two jets, reflecting different ice mixtures or different depths of origin. We should see dust properties change, reflecting different surface erosion patterns at the two poles, and we should see the jets evolve over time as the reservoirs deplete, as the structure changes, as the object continues to outgas and lose mass. Some of these predictions have been tested, some are still being evaluated as data comes in, and here's where the natural hypothesis faces challenges. The switch at perihelion was sharper than thermal models easily predict. The alignment stability is tighter than simple wobble models produce. The compositional data shows differences, but not dramatic ones. not the stark reservoir-to-reservoir variation you might expect if the two jets come from completely independent sources. The observations don't definitively rule out the natural explanation, but they strain it. They require fine-tuning the parameters, invoking additional factors, explaining why the predicted signals are weaker or different than the simple model suggests. This is where Occam's razor becomes relevant. The principle states that when you have competing explanations, you should prefer the one that makes the fewest assumptions. But applying Occam's razor isn't always straightforward, because what counts as an assumption depends on your framework. If you start with the assumption that interstellar objects are natural, then explaining 3i Atlas requires you to assume specific geometric configurations, compositional gradients, structural features, all of which are individually plausible but collectively unlikely. That's a lot of assumptions, but they're all assumptions about details, not about fundamental categories. If you start with the possibility that manufactured objects could exist in interstellar space, then explaining 3i Atlas requires you to assume that such objects can be made, that some civilization made them, that this one travelled to our solar system, and that it's behaving in ways consistent with designed functionality. That's fewer individual assumptions, but one of them is categorical, the existence of alien technology. And categorical assumptions carry weight. They shift entire worldviews. So which requires fewer assumptions? The answer depends on what you consider more probable, that nature produced an extreme outlier with 1 in billions odds, or that we're observing evidence of technology from beyond our solar system. Different people, applying the same logical principle, reach different conclusions based on their prior beliefs about the universe. And that's okay. That's how science works when you're at the frontier, when you're dealing with data that challenges existing frameworks. What the natural hypothesis needs, to become more convincing, is a mechanism. Not just a list of lucky coincidences, but a physical process that naturally produces this outcome, that makes the alignment and the switching more probable than the raw geometric calculations suggest. Maybe there's a feedback loop we haven't identified, where outgassing torques naturally stabilize the rotation axis toward the Sun, where the jet's own thrust creates the alignment it appears to be maintaining. Maybe there's a compositional or structural feature common to objects forming under certain conditions, a feature that predisposes them to polar venting and thermal switching. If such a mechanism exists, if it can be identified and verified, the natural explanation becomes much stronger. But as of now, that mechanism hasn't been convincingly demonstrated. The models require careful tuning. The parameters need to be set just so. And when a model requires that level of fine-tuning to match observations, it's a sign that maybe the model is incomplete, that there's something we're not accounting for. That missing piece could be a natural factor we haven't considered yet, some aspect of cometary physics that's rare but real. Or it could be an indication that the natural framework isn't sufficient, that we need to expand our thinking. I want to emphasize that this isn't about abandoning scientific conservatism. It's about honest evaluation. The natural hypothesis has merit. It's the default starting point, and rightly so. But it's facing challenges from the data, challenges that need to be acknowledged and addressed. And part of addressing them is considering alternatives, not because those alternatives are proven, but because they help clarify what evidence would distinguish between models. Comparison sharpens understanding, and right now we need all the clarity we can get. What we need next is to talk about what happens from here, about the observations that might resolve these questions and the timeline on which answers might emerge. Today matters. December 19th, 2025 matters, because this is the day when 3i Atlas reaches its closest approach to Earth, when the distance between this enigmatic object and our planet hits its minimum, when the observational geometry is as favourable as it's going to get. For astronomers, this is the moment they've been preparing for, the window of maximum opportunity, the time when telescopes can capture data with clarity and resolution that won't be available again as the object continues its journey outward. Distance determines detail. The farther away something is, the harder it becomes to resolve fine structure, to detect faint signals, to measure subtle variations. As 3i Atlas approaches Earth, it's been getting brighter in our telescopes, not because it's emitting more light, but because the light it reflects and emits has less distance to travel before reaching our instruments, and that means better signal-to-noise ratios, better spectroscopic data, better imaging, better everything. Today represents the peak of that improvement curve, but close approach is fleeting. The object is moving fast, over 20 kilometers per second relative to Earth. At that speed, the geometry changes rapidly. Tomorrow it will be farther away than today. Next week it will be noticeably dimmer. Next month it will be fading from the view of all but the largest telescopes. So the observations happening right now over these few days bracketing closest approach are precious. They're the data that will define our understanding of this object, the measurements that will either support or challenge the models, the evidence that future papers will cite for decades. What are those telescopes actually doing? Start with imaging. High-resolution cameras on observatories around the world and in space are capturing pictures of 3I Atlas and its jets, documenting their structure, their brightness, their orientation. These images will be analysed for changes, for asymmetries, for features that reveal internal activity. They'll be compared to images from earlier observation campaigns to track how the jets have evolved, whether their alignment has shifted, whether new features have appeared. Spectroscopy is equally critical. By splitting the light from the object into its component wavelengths, scientists can identify what elements and molecules are present in the gas and dust. Different compounds absorb and emit light at characteristic wavelengths, creating a spectral fingerprint. By reading that fingerprint, researchers can determine composition, can measure relative abundances, can infer temperature and density and flow velocity. Spectroscopic data from today's observations will tell us whether the two jets have identical chemistry or whether there are differences that point to separate reservoirs. Infrared observations add another layer. Thermal emission, the heat radiated by the object's surface, peaks in the infrared part of the spectrum. Mapping that emission tells us about temperature distribution, about where the surface is hottest, about how heat flows through the interior. If the dual-pole model is correct, we should see thermal signatures at both poles. If there are insulating layers channeling heat to specific vents, the thermal map should show patterns consistent with that structure. Infrared data can, in principle, reveal the underlying architecture. Radio observations are less conventional for cometary studies, but they're part of the campaign for 3I Atlas. Radio telescopes can detect emissions from certain molecules, can probe the gas cloud around the nucleus, can search for signals that might indicate anything unusual. No one is seriously expecting to find a radio beacon, but the absence of any anomalous emission is itself useful data. It constrains what the object is not, even as we debate what it is. Then there's astrometry, the precise measurement of position and motion. By tracking exactly where 3I Atlas is at each moment, astronomers can refine its trajectory, can measure the non-gravitational acceleration with higher accuracy, can detect any changes in its motion that might indicate variable outgassing or other forces. Astrometric data from close approach will reduce the uncertainties, will tighten the constraints, will make the velocity anomaly calculation more precise. Over the next several weeks, this data will be processed. Raw telescope images will be calibrated, corrected for instrumental effects, combined to increase signal. Spectra will be analysed, line identifications confirmed, abundance calculations performed. Thermal maps will be constructed, models fitted, comparisons made. It's painstaking work, but it's essential work, and it's the work that transforms photons collected by mirrors and detectors into scientific understanding. Some results will come quickly. Preliminary images and spectra might be released within days, giving the community and the public a first look at what was found. But detailed analysis takes time. Peer review takes time. Papers presenting comprehensive findings might not appear until months from now. That's the pace of science, and it's worth the wait because rushed analysis leads to mistakes, leads to misinterpretations, leads to claims that don't hold up under scrutiny. What could these observations tell us that would shift the debate? If the data shows clear evidence of wobble in the jet alignment, if the sunward lock isn't as tight as it appeared in earlier observations that would support the natural hypothesis, it would suggest that we were seeing a phase of temporarily good alignment, a lucky observation window rather than sustained precision. The natural model could accommodate that, could explain it as the object passing through an orientation where the vent happened to be well aligned for a period before precession or rotation changes shifted it. If the thermal mapping reveals hotspots at both poles with evidence of deep channels, connecting them to surface vents that would support the structured interior version of the natural model, it would show that the object does indeed have the architecture needed to produce the observed behaviour through passive thermal processes. It wouldn't eliminate all the probability concerns, but it would make the natural explanation more mechanistically satisfying. If spectroscopy shows that the two jets have significantly different compositions, that would indicate separate reservoirs with different formation histories, which is consistent with the dual pole switching being a response to different ice mixtures sublimating at different temperatures. That's a specific prediction of one version of the natural model, and confirming it would lend credence to that interpretation. On the other hand, if the alignment remains stable beyond what models predict, if there's no wobble, no precession, no drift over the observation period, that would deepen the mystery. It would suggest that whatever is maintaining the alignment is more robust than polar vent geometry can easily explain. It would push the natural model into requiring even more specific conditions, even more fine-tuned parameters. If the thermal data shows unexpected patterns, if there are heat sources or sinks that don't match passive solar heating, that would be significant. It wouldn't immediately imply artificial origin, because there could be exotic natural processes we haven't considered, but it would require explanation, would open new questions about what's happening inside the object. If any instrumentation detects signals that are anomalous, that don't fit the cometary profile, that suggest organized emission rather than natural thermal or chemical processes, that would be paradigm challenging. But the threshold for such a claim is high, appropriately high, because extraordinary claims demand extraordinary evidence. Ambiguous signals wouldn't be enough. Clear, repeatable, independently verified anomalies would be needed. Realistically, what we're most likely to see is incremental clarification. Some questions will be answered, the composition will be better characterized, the rotation period will be refined, the thermal profile will be mapped, and from those answers, new questions will emerge. That's how science progresses at the frontier. You don't usually get sudden definitive revelations. You get a gradual sharpening of understanding, a slow convergence toward models that fit the data better and better. But there's always the possibility of surprise. There's always the chance that an observation will reveal something completely unexpected, something that doesn't fit any of the existing frameworks, something that forces a rethink. And given how unusual 3i Atlas has been at every stage of its observation, given how many times it's defied initial predictions, we should remain open to being surprised again. For those of us watching from outside the professional astronomy community, for everyone fascinated by this story, the coming weeks and months will be a time of waiting and anticipation. The data exists now, captured by those telescopes, stored in archives, waiting to be analysed. The answers, or at least better questions, are in there. We just have to be patient while the experts do their work, while they apply their tools and their expertise, while they debate and discuss and refine their interpretations. And as that process unfolds, we'll learn not just about this one object, but about the broader universe we inhabit, about what's possible, about what's out there travelling between the stars. Which brings us to the final question, the one that ties everything together and sets the stage for whatever comes next. So here we are, standing at the edge of what we know, looking out at something that challenges our categories, that sits uncomfortably between natural and extraordinary, that refuses to fit neatly into the boxes we've constructed to make sense of the cosmos. And the question we're left with isn't whether 3i Atlas is definitely one thing or another. The question is whether we're willing to ask honestly, to look at the data without predetermined conclusions, to follow the evidence wherever it leads, even if that destination is uncomfortable. Can we still call this a comet? That's not just a semantic question. It's a question about how we understand the natural world, about what categories mean, about where the boundaries lie between the familiar and the unprecedented. Comets are icy bodies. They sublimate when heated. They produce jets and tails. By those definitions, 3i Atlas qualifies. It outgasses. It responds to solar heating. It displays all the surface characteristics we associate with cometary activity. But comets don't maintain precision orientation. They don't switch active regions with geometric timing. They don't align their jets with probabilities in the billions. They don't accumulate constellation after constellation of anomalous behaviours, each one individually explainable but collectively straining the natural model to its limits. So is it still a comet if it does all those things? Or does the label become misleading, become a category that obscures rather than clarifies? I don't have a definitive answer. I don't think anyone does yet. What I have is the data, the observations, the measurements that don't care what we call them. The jets are aligned, the probabilities are calculated, the switching occurred. Those are facts documented and verified. The interpretation, the model we use to explain those facts, is where the uncertainty lives. And that uncertainty is not a weakness. It's the space where discovery happens, where understanding grows, where science does its most important work. There are two paths forward from here, two interpretations that remain viable given current evidence. The first is that 3i Atlas represents an extreme natural outlier, a 1 in billions, configuration that we happen to be witnessing because the universe is vast and even wildly improbable events manifest somewhere. This interpretation preserves the existing framework, acknowledges the rarity, and continues to work within the physics and chemistry we understand. It's conservative in the best sense of that word, meaning it conserves the models that have served us well and extends them to cover edge cases. The second is that we're observing evidence of structure that wasn't naturally formed, that carries signatures of intent, of design, of purpose. This interpretation doesn't require believing in alien visitors waving at us or trying to communicate. It simply acknowledges that in a universe billions of years old, containing billions of galaxies each with billions of stars, the emergence of technology capable of travelling between those stars is not only possible, but perhaps inevitable. And if such technology exists, if it travels, if it explores or monitors or migrates, then occasionally we should expect to encounter it. And it might look like this, like an object that functions too well, that maintains tolerances too precisely, that behaves with coherence that natural chaos rarely produces. Both interpretations have merit. Both are worth serious consideration. And the way to distinguish between them isn't through philosophy or belief. It's through continued observation, through gathering more data, through testing predictions, through the patient application of the scientific method. We need more telescope time. We need better instruments. We need long-term tracking to see how the object's behavior evolves. We need independent verification of every anomalous measurement to ensure we're not chasing artifacts or errors. What I can tell you with confidence is that the discussion is legitimate. The questions being raised by 3i Atlas aren't fringe speculation. They're mainstream scientific inquiry into an object that defies easy explanation. The papers being published, the conferences being held, the debates happening among experts, all reflect genuine uncertainty about what we're observing. And that uncertainty is healthy. It's the sign of a scientific community willing to confront data that challenges assumptions, willing to consider alternatives, willing to update beliefs when evidence demands it. For you, watching this unfold, participating as an informed observer, the opportunity is to witness how science works in real time. You're not reading about a discovery made decades ago and settled into consensus. You're watching the process of discovery as it happens, seeing the data come in, seeing the models compete, seeing the debate evolve. That's rare. That's special. And it's a reminder that our understanding of the universe isn't fixed, isn't complete, isn't settled. It's dynamic, growing, responsive to new information. The 15th Anomaly, this dual-pole sunward lock with its perihelion switching, is significant not because it proves anything definitively, but because it sharpens the question. It adds precision to the puzzle. It provides a specific behavior that models need to explain, a target that tests both natural and alternative hypotheses. And as more data arrives, as analysis continues, we'll see which models survive that test and which need revision. I want to leave you with a sense of wonder, because that's what this object deserves. Whether it turns out to be an extraordinary comet or something else entirely, it's teaching us about possibilities we hadn't fully considered. It's pushing the boundaries of what we thought we understood. It's reminding us that the universe is larger and stranger and more diverse than our theories capture. And that's a gift, an invitation to remain curious, to stay humble, to keep asking questions even when the answers aren't immediately clear. If this investigation resonates with you, if you want to follow the story as it develops, make sure you're subscribed to this channel because we'll be covering every major update. When new papers are published, when observation campaigns report findings, when the scientific community reaches new conclusions, we'll be here to break it down, to explain what it means to continue this conversation. Hit that like button if you found this deep dive valuable, because it tells me that there's an audience for this kind of detailed, thoughtful analysis, for content that respects your intelligence and your curiosity. And drop a comment. Tell me where you stand on this. Are you convinced by the natural explanation, or do you think there's something more going on? What observations would change your mind? What questions do you wish we could answer? This isn't a monologue, it's a dialogue, and your perspective is part of the process, part of how we collectively make sense of extraordinary phenomena. 3i Atlas is out there right now, moving through space, continuing its journey that will eventually take it back into the darkness between stars. We had this brief window to observe it, to study it, to learn what we could. And what we learned is that the universe still holds surprises, still presents us with observations that challenge our models, still invites us to look deeper, think harder, question more carefully. The 15th Anomaly just changed everything because it gave us precision to ponder, because it showed us behaviour that demands explanation, because it forced us to confront the limits of our current understanding. Whether that leads to refined natural models or to paradigm-shifting discoveries, we'll find out together. The data is being collected, the analysis is underway, the answers, whatever they are coming, and that's where we leave it for now. Not with conclusions, but with questions. Not with certainty, but with curiosity. Not with the end of the investigation, but with the recognition that we're in the middle of something significant, something that might reshape how we think about what travels through the cosmos. Stay curious, stay skeptical, stay engaged, because this is how we learn. This is how we grow. This is how we discover what's really out there, waiting to be understood.